Welcome to my presentation. My name is Richard Potter. Today, I'm going to give a demonstration of the DOE Toolkit, which is an add-on for Wolfram Mathematica that was created by my company, Harper Corditt Software. Design of experiments continues to be of great importance in scientific research, and the need to be able to produce a good experimental design has been addressed in several statistical software applications, such as Minitab. However, the Wolfram language itself does not really provide any predefined functions that generate experimental designs. And so that's where my DOE toolkit comes in, essentially as a supplement to Mathematica. Now, I should mention that the DOE toolkit does not teach you how to design an experiment. Instead, we assume that you already know what type of design is going to be appropriate for the experiment that you are conducting. And then at that point, you will be able to pick out the appropriate function provided by the DOE toolkit to generate the design that you need. The DOE toolkit supports all of the classic design methodologies. In the category of screening, we support full factorial and fractional factorial designs. For the methodology known as response surface, we generate box-Benken and central composite designs. We also provide mixture designs and orthogonal designs. Now, regardless of what DOE toolkit function you use to create your design, the result will always be encapsulated in a Mathematica dataset object. The Mathematica dataset object is a very, very powerful feature of Wolfram Mathematica, and we feel it's really important that when we generate your design, we encapsulate it in such an object, because then you can leverage all the power of the dataset technology in Mathematica to modify and manipulate your data within the data set, as well as to analyze the design. Excuse me. Once you've generated a design, the DOE toolkit provides a function that allows you to augment your design. So you can randomize the runs, you can replicate the runs, and you can add blocking to your design, which is usually a recommended thing to do. In addition, for certain designs, it makes a lot of sense that you may want to add central points and or axial points. Now, sometimes when you generate a design, the number of runs that are created may be more than you want to handle. And in that case, it becomes useful if you can intelligently pick out a proper subset of the original set of runs and perform your experiment based on that subset. To support that procedure, we provide the optimizer tool, which once you've got the design generated, you can run the optimizer and specify what kind of optimality criterion needs to be applied in order to select a subset of the runs. In addition, I won't have time to demonstrate this last feature, but I did want to mention it. We also provide a tool called a desirability manipulator. And as the name suggests, it's built upon Mathematica's incredible manipulate function. And it gives you a nice graphical user interface in which you can, once you've conducted your experiment and have some results, you can start playing what if scenarios by asking, well, what if I change the factor setting of this particular factor? What will that do to the desirability value of my model? And you can define your we provide a predefined desirability function, but you can also define your own desirability function. So let me turn now to actually giving a demo of the DOE toolkit in action. As I mentioned, this is an add-on to Mathematica, and therefore you have to load it into your notebook. And by loading it into your notebook, then the definitions that are contained in the toolkit become available to your Mathematica notebook. Because this is an add-on, the file that contains the DOE Toolkit has a .wl file extension, which stands for Wolfram language. So to load an add-on into your Wolfram notebook, you typically would evaluate the get function, and you'd provide it a path to the DOE Toolkit on your particular hard drive. And once it's loaded, then all of the functions defined in the DOE Toolkit are now available for you to call upon. In this first example, I'm going to create a full factorial design using the DOE factorial function. All of the functions that the DOE Toolkit provides are pretty standard in terms of the interface that they employ. With one exception, all of the other functions require you to provide two input arguments. One is a list of factors that are involved in the model. And the list in this case of factors is always just a list of names. In this case, and in all of my examples, I'm just calling the factors x1, x2, etc. In addition, you provide a second list, which is a list of levels. Now the levels list is a list of lists. So, and in each sublist, you provide the number, or excuse me, the values of the levels that the associated factor can assume. So in this example, the factor x1 can assume three different levels, 0.7, 1.9, and 3.1. So when I do this, before I actually evaluate the DOE factorial, I want to see a few other things. First of all, you'll notice that I have specified an option, randomize runs, and I've set it to false. There are lots and lots of options that you can set in any of the DOE Toolkit functions. This one is a little bit strange, and you may be wondering, why on earth would you do that? Because most people who are involved in experimental design know that the best practice is always to randomize the runs in your design. Well, the reason why I'm doing that today is because in particular for some designs like a factorial, there will be a patterns column that appears in the design, in the resulting design, and you can then just eyeball that yourself and you can verify, okay, he does have the right number of runs generated, and the pattern column shows me that he has covered every possible combination of levels for the given factors. Now, by default, the randomized runs option is always set to true, so really using this in the real world, you never even have to worry about this option. But for the sake of providing a demo that's a little bit more humanly readable, I've got this option set to false. One last thing before I evaluate this particular example, you'll notice that the DOE factorial function returns an object, which I call an X design. In this case, it's named full fact X design. An X design is really just, X design is short for extended design. And it's really just a two-element list. The first element in the list is a dataset object. It is a dataset object, excuse me. And the second element in the list is a list of metadata. So if I evaluate this, you'll see it generates a Mathematica dataset object, which indeed has 27 runs, which is what you'd expect in a full factorial. We've got three factors, each of which has three levels. So it would, naturally you'd expect to see 27 runs, and indeed they are present. And if you examine the pattern column, which is just showing me the indices of what level of each factor is involved in this particular run. So the first run clearly shows me that, okay, in this run, it's the first level of each of the three factors that's appearing. Oh, and by the way, each of these DOE Toolkit functions will warn you if you fail to randomize the design, because like I say, that best practices dictate you always want to randomize your runs. And then the metadata, which is the second part of the X design, is just a bunch of information that helps you to keep track of, okay, what's involved in this design that I generated? Because if you come back to it later, it might be expensive in some cases to regenerate your design. And in this case, you can, if you can't remember what went into constructing this design, you can check the metadata. Also, you can customize the metadata. So by default, you're going to get a bunch of fairly useful information, but you can also customize it. There's an option to do that, which I won't bother to demonstrate in this particular case. Now, with any DOE toolkit design that's been generated, you can always add blocking to the design. So in this case, I'm excuse me, using a slightly simpler example. I've got 3 factors, each of which has 3 levels. Once again, I'm not going to randomize the runs. In fact, that's going to hold for the remainder of this demo, so just keep that in mind. But I am going to specify this option that you haven't seen before, the blocking option. And I'm going to say, basically add a new column called plot, and there's going to be 2 blocks. And so the resulting design basically is contains the same original 8 runs as you'd expect, and then another 8 runs for block number 2. So one nice thing about the dataset technology is you can add all sorts of really cool graphical components, including, in this case, a background color. So it's very easy to spot, okay, the top 8 runs are block number 1, and the second block is in the second 8 runs. In addition to blocking and randomizing and replicating, you can also represent the data factor levels as well as the patterns in various ways. So in this example, rather than using what is kind of traditional, which is, say, for a 2-level factor, you might have +1 and -1 to represent its levels, or if it's a 3-level factor, you might have -1, 0, and 1. We decided that it might be nice in some cases to give the user the free ability to specify, to represent things symbolically in all sorts of different ways. So in this case, I've instructed the DOE Toolkit to represent the pattern that's present in each run using colors. And the values or the levels of each factor are represented, well, for the 2-level factors, x1 and x3, I'm using -1 and -1 to represent whether it's the lowest value or the highest value of the particular factor. But in the column for x2, which is a 3-level factor, I'm using clubs, diamonds, and hearts to represent those different levels of that factor. So the next type of design that we support is a fractional factorial design. And the only difference between fractional factorial and the full factorial is that there's an additional option that we support, which allows you to specify confounding rules. So in this case, I've got 3 factors, x1 through x3. Each of the factors can assume any of 3 different levels, but I'm going to specify a confounding rule, which basically tells the DOE Toolkit to confound x3 with the factors x1 and x2. Now you can also specify your own interaction tables, so you can customize how confounding works, how interaction really takes place. But in this case, I'm just using the built-in interaction tables, and I'm specifying this confounding rule. And so when I do that, I get back, even though I have, a full factorial would have generated 27 runs because I got 3 factors with 3 levels each. In this case, I only have 9 factors, and 9 runs, excuse me. And that's because in each of these runs, x3 is really, the value of x3 is based upon confounding the values for the levels of x1 and x2. Another type of methodology that's very popular in design of experiments is response surface. Box-Benken is a very classic example of this. It's always assumed that your factors always have 3 levels each. And so with Box-Benken, you get a design that's not a factorial, but it does help to reduce the number of runs, which I should have mentioned this earlier. In case of the fractional factorial, the whole name of the game there is to reduce the number of runs, and confounding one effect with others is how that happens. Central composite. With central composite, that's used for specific type of experiments. You can have central points, which help to balance the design. And you can also have axial point groups where you can specify alpha. You have different choices for determining how alpha is computed. You can ask for alpha to be rotatable, orthogonal, or spherical. And so once again, you specify your factors, you specify the levels. Usually the factors are going to usually be 2 levels each. And then when you do that, you generate a design in which you have your axial point group at the top. By the way, you can specify where you want the axial point group to be included. In this case, I said put it at the top. And then at the bottom of the design, you've got your central points. Another type of design that we support is mixture design. In this case, this is the one exception to the general rule. You don't specify levels for the factors, you just specify the factors. And in terms of the mixture designs that we support, you can create either a simplex lattice or a simplex centroid. In this case, I'm doing simplex lattice. And one thing that I think is kind of cool about this particular design is that for mixture, in the pattern column, rather than just, since you don't specify levels, we use histograms to specify, what's going on in each run in terms of what factors are involved in this particular run of the 3 factors. Next type of design that we generate is orthogonal. Typically with orthogonal, each factor will either have 2 levels or 3 levels. In this case, we're doing a pretty elementary example where we have 4 factors and each of them assumes 1 of 2 different levels. And so when I evaluate that, I wind up with a design that consists of 8 runs. In this case, one of the things that we achieve and are targeting in any case is that the runs should be balanced and mutually orthogonal. And now we come to optimization. As I mentioned earlier, you might start out by using one of the DOE Toolkit functions to generate a design, but the design that's generated might be too big. In some sense of cost, it might just be cost prohibitive to try to conduct an experiment in which every run in the original design is actually executed. And so what will often happen is you create a design, and that's what I'm going to do in this example. I'm going to create a 4-factor design in which each factor has 3 levels. When I do that, I get back this Mathematica dataset object that has 81 runs in it, as you can see. And it might just not be, it might just be impractical to try to actually conduct the experiment and, measure for each of these possible combinations of these 4 factors, all of these different levels. Just might not be reasonable at all. And so somehow you have to try to come up with a proper subset of those runs in this 81 run full factorial. You want to somehow or other pick out a proper subset of those runs that still is, in terms of picking out a subset, it is in some sense or other the best subset that could be used from the original set of runs. And so what you can do with the DOE optimal function is you can specify, okay, given another design that's already been generated and plugging that as input, and I should mention, like, okay, so I've used the DOE factorial function and it's returned a full fact xdsn3 object. Okay, so what I do then is I take that object and provide it as input to the DOE optimal function, and I also specify the number of runs I want in the optimal design matrix that's going to be generated by DOE optimal. And I also specify what optimality criterion I want to use. We support D optimal designs, A optimal, T optimal, and G optimal. Those are the 4 standard optimality criteria, and you can specify any one of those 4. And in terms of the algorithm that's employed, we support, and you can choose, there are options to do this. You can indicate whether you want us to use row exchange or coordinate exchange or exhaustive. Of course, exhaustive, if you choose that, that's going to be very expensive, because then we're going to check every 40 run proper subset of the original design to see how it fares against your optimality criterion. So in this case, I'm specifying that I want D optimal as my criterion. And you'll notice down below, I mean, it went by pretty fast, but you may have noticed that there was a brief moment where there was a little progress bar that was displayed. This particular function, and this is also true of the DOE orthogonal that I just demonstrated earlier, these 2 functions are slightly different. They're a little bit more interactive than the other ones, because it is possible while the evaluation is underway to use the abort key sequence that's appropriate for your operating system to tell the DOE toolkit, hey, just stop. You know, like in particular, if you're doing an exhaustive search for the very best D-optimal 40 run subset, it might take a really long time, and you might not want to do that. And so if at any point you need to terminate or you wish to stop, you can hit your abort key sequence on your device and it will stop. And then it will report back to you, okay, at that point in time, right before you aborted the search algorithm, here was the very best subset I'd come up with at that point. So that's fairly useful. And in this case, the metadata tells us that after using row exchange and applying the D-optimal criterion, the best that we could do to maximize the absolute value of the determinant of the X prime X matrix was to come up with approximately 1.2 times 10 to the 13th power for the value of the determinant of the X prime X matrix. Well, that concludes my demo. I want to thank everybody for watching. I really appreciate your coming to my demo. I do appreciate feedback. So if you have any suggestions or things you'd like to see in the DOE Toolkit or any questions, you can always contact me at this email address down below. And I would like to mention that if you're interested in taking the DOE Toolkit for a test drive, you can do that because there's a fully functional demo at my website, www.harpercordittsoftware.com, and you can download the demo and it's fully functional and you can check it out and see whether you like it or not. And last but not least, here's a barcode image for my the link to this actual presentation notebook. So are there any questions? So the first question is, how is your DOE toolkit provided as an add-on to Mathematica? Is it a packlet? The answer is no. It is provided as a Wolfram language package file. It's not a packlet because right now the Wolfram research has not provided any kind of mechanism for uploading something as a packlet that still provides kind of protection for your intellectual property. Obviously, I mean, I haven't made any secret of this. This toolkit is something I'm selling as an enhancement to Mathematica, and therefore I can't upload it as a packlet right now to the packlet repository because you can't put anything that's up there that's encoded, and my toolkit is something that's encoded. So, in other words, I don't expose my actual code in the toolkit WL file. So I hope that answers that question. The second question that someone asked was, it says, I am not familiar with the 4 DOE methodologies you mentioned. What would you recommend to learn about these 4 methodologies? Well, there are several really good books out there that I could provide you references to. Let me see if I can bring up my user guide. The DOE Toolkit comes with a really nice PDF user guide, and at the very end it has a bunch of references. Some of the references cover the scientific journal articles that we referenced in order to implement the algorithms, because like I said, we didn't invent any of these algorithms. These are all algorithms that people have, research scientists, people who are PhDs in the field, have described the algorithms, and we read those articles, studied them very carefully, and then we implemented them in Mathematica. And so, but one of the things I recommend, and so I've given you those references as well as some suggestions for reading, and one of them that's really the best is the Engineering Statistics Handbook, which is provided by the National Institute of Standards and Technology, otherwise known as NIST. And their website is www.itl.nist.gov. So that's www.itl.nist.gov. And I would recommend going there. They're also in my DOE user guide. I provide some suggestions of other books that are fairly straightforward and easy to understand, that if you want to get started on design of experiments, the books that are listed there in my DOE user guide will be very helpful references. The next question is, this is really interesting. We, in parentheses, as resellers of Minitab in Germany, NPRIN, have the challenge from time to time to offer our customers a replacement for Minitab. Is there a wrapper for your tool, perhaps as a web app or Excel add-in? Sadly, no. I'm afraid that is not the case. But one thing I would like to point out is, now with the DOE Toolkit and the extremely powerful functionality that Mathematica provides within its statistics functional set, you can do just about anything you want to that requires statistical analysis. You no longer have to go to some other application like Minitab or SAS or whatever, SPSS. You can do everything you need to do with very, very few exceptions. You can design your experiment from within your notebook in Mathematica, and then you can run your experiment and come back to your notebook and input the experimental results and analyze your data, constructing very complicated models, all using Mathematica's incredible set of statistical functions. So I'm sorry I don't have a wrapper for the tool, but that's just the way it is. Another question is, what are examples of the type of users for your DOE toolkit? Is it academic scientists or people in big pharma? The answer is it could be anybody who's trying to design an experiment that needs some kind of assistance and guidance. There are people in academia right now that could find it useful. Right now, the people that have actually purchased the DOE toolkit in the past have been people who are actually in industry, and they're using it for, well, I'm not allowed to say what they're using it for, but it is being used in industry. I don't have any big pharma customers. And then the last question is, after making a design and running the experiments, do you have the tools that make it easy to enter the results? Okay, that's a very good question. I do not provide any tools that let you, okay, let me start over. The dataset object is really beautiful. It does have one slight drawback in that it's not really easy to modify, especially not with the user interaction kind of GUI interface that we might expect, like an Excel spreadsheet or something. I know that there's an experimental function that that Wolfram is working on, which would I believe the purpose is to make give you sort of an Excel or a data set object presentation in your notebook that you can actually click on and modify in real time in place. And that would be ideal for the kind of workflow that takes place when you're doing experimental design, because you design your experiment, you learn the runs you need to perform, you go do the experiment, you do those runs, you come back with your data, and now it would be really nice to be able to enter those into your data set object. Well, you can do that. I provide functions in the DOE Toolkit, and I provide lots of documentation that explains to you how you can do that. How do you add a column or add a row to your data set object that allows you to enter the values that you have recorded after performing the experiment. But hopefully in future reversions of Wolfram's Mathematica, that dynamic, or whatever they're going to call it, spreadsheet object, or whatever they're going to call it, where you can modify it in place, that will be the perfect mechanism for entering the results. But right now, the best I can do is I have very clear examples in my documentation that show you, okay, you need to add a column for recording the results of this run. Here's how you add a column to a data set object, and here's how you modify the cells in each row, and so on. So these are really good questions. I thank everybody for providing these questions. And once again, I want to say thank you to Wolfram Research for letting me present this demonstration today. And thank you to Stephen Wolfram and all the people at Wolfram Research for creating this marvelous artifact from the future that we all know and love as Wolfram Mathematica. Thanks, everybody. Goodbye.